Hello everyone, I'm Akshita Bindal and today we are going to study attention economics. So as discussed earlier, today we were going to study A/B testing. Previous slides, kindly read it or go through my previous videos. Today's lecture is a bit lengthy. So let's begin from the beginning. In 1920s, statisticians and biologists like mm, statistician and biologist this person like Ronald Fisher discovered the most important principle behind A/B testing and randomized control experiment in general. He wasn't the first one to run an experiment like this, but he was the first to figure out the basic principles and mathematics behind it. So he had a farm plot and he wanted to test two fertilizers and which fertilizers gave a better yield. So what did he did? He did was like he said, okay, for one crop cycle I have to do fertilizer A, and for another crop cycle I will have to do fertilizer B. And he asked questions. What happens if I put fertilizer A on this land, more of it, more of A on this land, and if I put less of B on this land. So basically, they were testing them, and that was requiring a crop cycle time, and that was at that time. Fast forward to 2016-18, where data is cheap, real time, and anyone can be practitioner. Not a someone who is statistician or very technical person requires to be. So continuous monitoring of the test results were done, and it was it was preferred to have a adaptive sample size testing. Now, what is A/B testing? Simply put, it's a practice of using randomized experiments to make decisions, and it can be any decisions, business decisions, any kind of decisions. In basic statistics, we studied type 1 error, type 2 error, where type 1 error was false positive and type 2 error was false negative. We have to minimize both the error. Both the errors are not good for us. For we have set certain powers for it, like power of test was initially set up at 90 and then it was decreased to 80. However, my main focus would be on false positive, but of course we have to minimize both of them. This is the basics that we studied. Then now the question arises, when is it that we say it's an A/B testing? It's an A/B testing when it's randomized, because randomization means causal inference, and causal inference is cause and effect relationship. And why is it difficult? Because you have to separate your actions from the other factors. Now, what are the other factors that may affect this? This can be whether competition, business cycles, COVID, force majeure, the COVID, that is anything that can affect, but you want to test your controlled methods. Now, before jumping to next slide, I would just like to quickly tell you about that. It's A/B testing because there are two methods. When there are three methods and you are not sure which one to apply, it would be ABC testing. When there are n methods, it would be ABC, D, E, F, so on up to n testing. So unless and until there is randomization and control, no, it won't be called as A/B testing. Now let's study a case. Case 1, your action determines customer action, easy. But there are other factors like day of the month, week, weather, marketing campaigns, competitor strategy. And then we can consider behavioral factors like anchoring, framing, references. That is something that needs to be quantified, and then there would be different methods for it. But how does randomization helps? it helps us if suppose A and B and we have got two designs, then we assign half of the people to one half and half of the people to other half. Now this will help us to average out that confounding factor. And what was that confounding factor that we have studied in our previous slides? So we want the thing that is under your control. uh, so we want to only study that effect. Now we can control them explicitly with the large enough data set within it, with large enough of sample set, and those factors should statistically average out and be equal between the customers who saw the version A and who saw the version B. So the factors should be, the confounding factors should be averaged out between group A and group B. Now the question arises, what could be tested and what should you test? Like, now that depends upon businesses to businesses, industry to industry, context to context. Something that worked for a voting campaign may not work for a business website. Simple. If something is working for A, may not work out for B. So how can we how can we get results then? So a simple way out is systematic experimentation, which will help you learn which component of your website or service matters the most. And everything is done by testing softwares. um, Initially, like 20 years ago, it used to be humans. The results were for humans, and they have to do the evaluation and the implementation, and they have to make decision factor is still in their hand because cost is in their hand. But otherwise, human interference has decreased. 20 years ago, when Facebook, Twitter, Microsoft, Amazon used this, human interference was a little more. Now, how does statistics helps? It helps. We will discuss it further also, but in generally, it provides a principled way to quantify how certain you should be about your results. Double quotes, the magnitude of effect you observe and your sample size. That is the main purview. There is a there is a fundamental trade-off between precision and time. So with large sample there is more precision, but with smaller sample there is speed, and with speed there is less time. So how can you solve this trade-off? Maybe uh, for hypothesis testing we can have a precision mindset, like a large sample set, and for metric optimization we can use a smaller sample size. But why do we need to study the false positive? Because this would be costly for the businesses. If we accept something that is not true, then both for optimization and hypothesis testing, it would create some blunders. So what is the way out? That we try to do AA testing. Like, we know what results we want, so we say that there is no difference between A and B. So we run a AA test to understand how good our test is. Now, A/B testing is also kind of a randomized experiment, and randomized control trials that is used by testing companies, web applications. So typical use cases when we compare two web versions, like which has a higher conversion rate and which has a lower conversion rate. Now, as per Stanford University professor Ramesh Johari, the problem in peaking in A/B testing is to decide whether to continue the experiment or not. And this can dramatically inflate the false positive. Now, what is being plotted over here is false positive probability, and I'm stopping first time the p-value is below a cutoff. Now we have three curves. One is at 1%, one is at second 5%, and third is at 10% with 10,000 number of observations. Now at 1% you have 20% inflation at false positive. So that's a huge amount. Then you have 40% inflation, 60% inflation. So it's like when to it's like you have 20% inflation, then 40% inflation, and then 60% inflation, and then we have to find that what would the user like to do. She chooses to stop adaptively to trade test length against detection of true positives. True positives would be the green boxes, to trade the test length against the detection of true positives. At the time, if the p-value is small enough, result is declared significant. So यही होता है कि p-value is less than 1%. Its significance, the significance levels that we study. And yeah, so I hope it's like you're able to understand what I'm saying right now, and it's not going above the head. So now here is a graph of 1 minus p-value, that is alpha, like 1 minus alpha, that is the confidence level. The graph is high, then the p-value is low. Now a red line over here, like this one, this is the red line over here, yahan par it's a red line. Now that red line is p is equal to 5% cutoff. Above and above that is like 95% significance. Like a false positive is 5%. So why do we run AA test? Because we already know the answer. Still there is false positive, and so so the two things which are supposed to be same are not same in AA testing, and this is kind of a problem because false positive is coming. So we try to have a fixed sample size, optimally balances the false positive and the true positive, but it is not adaptive, and adaptive testing can massively inflate the false positive. So what do we do? Now there are two views that comes from his audience, is that read the RTFM approach. Why doesn't user just apply the fixed horizontal stats property? Now when we reconciliation of this approach, change the change of p-value is what is suggested, right? And allowing the user to continuously monitor the test and report always a valid p-value. No matter how the user chooses to stop the test, no more than 5% false positive probability would come. So what do they do is that they provide a near optimal balance between test length and detection of true positives while controlling false positive and allowing the user to be adaptive. Avoid peaking at p-value. What does that mean? So it means that no decision should be there before completion of the experiment. Otherwise, there would be wrong conclusion, chances of wrong conclusion, chances of false positive. I hope it's clear. Now let's look at a little bit of statistical background. Now my goal is to figure out what the mean was. Given the mean is m, and more of the sample I have, the closer is to the mean I get. Now suppose I have x1, x2, x3, so on up to xn are the n number of independent variables, such that following a normal distribution with mean m, variance 1. Now standard error is proportional to 1 by under root n, that is the tolerance which we are willing to accept. Now we plot it against t. Now this is the t time period. we plot to find out if m is different from 0 or not. Now if m is not different from 0 and m is actually 0, but I declare it to be 0, that's false positive. And if m is different from 0 and I fail to detect that, then that's false negative. We have to control both of them. So do a good job on both the sides. Now, problem is if I claim that I am going to stop the first time the p value is below 0.05, it's the first time it crosses 1 by square root of n. And this is the dotted line that's plotted 1 by square root of n. But in probability, we have a theory. And that theory says that this line is gonna be crossed infinite times under the assumption that true mean was 0. It's like how we study about the true mean and the actual mean, and both are same or not. So this is a theory that we studied in statistics. It's for like, just refer to VK Ori, you'll get a catch of it, and if you do not, then I'll just help you out in that as well. So now when we study the actual mean and the true mean, it's just the mean and the 0. So this dotted line is over there, and now this is just we are taking 1 upon under root n, and if this is like the time is infinite, then this is, that is, type 1 error is going to occur. But now under the assumption that that the true mean was 0, so there would be a lot more conservative boundary. So see, this is like two things that we are avoiding, the negatives and the negatives. So we want our result to lie between. So normal distribution, maybe we used to do this only now. Then we have 5% significance, 1% sigma limits that we used to say, 2 sigma limits, 3 sigma limits, and 6 sigma limits. So we want to optimize our result till 6 sigma limits, like this only we used to study. So it's the similar thing, nothing very difficult sort of thing. But one thing is that the approximation that we takes is k delta to log n over n. So the k is the constant which can be adjusted, and this constant bounds the probability alpha and probability of the false positive, and variance might not be known. So the result actually says that the square root of log n over n is gonna be crossed infinitely times, which expands our boundaries to even more farther. That is the solid black line that we saw above the dotted line. And if mean is 0, then crossing the black line probability is strictly less than 1. We used to put a limit to it. So when we have tilde constant in front, I can adjust the probability, which is my false positive. That is for type 1 error probability. So what do we adjust? We adjust the constant. And constant is adjusted to avoid the crossing of the boundaries. Now let's say a user have targeted alpha, that is false positive probability, right? And then what we do is say is that the rule is to stop first time the sample mean crosses the constant times tilde square root of log n divided by n, and can guarantee alpha if constant is right. Okay, and then if the truth is different from 0, if the true mean is different from the actual mean, this rule is guaranteed to detect it eventually. And then how we get a p-value out of it is that time has a name T alpha at n time, and was rule was that we give is T value at a. Now, when our boundary is crossed of P value, then at that time we give this a name, that is T alpha. T alpha, what was that? The time at which you stop, the time when the value crosses the boundary line. That is, with the right constant being chosen, rule we give is that any p value at given n is the lowest alpha, such that the T alpha was beforehand. So for every alpha there is a T alpha. So for every corresponding alpha there is a T alpha. Some of them has not happened yet. Okay, and of course they are nested. So you are gonna get more conservative when alpha gets smaller. So so you would say what is the smallest alpha at which I would have stopped by now, and that's the p value we display. Now we create a version of likelihood ratios between the alternative and the null hypothesis, and what you are looking is for how large the likelihood statistics is relative to 1 over alpha, and so you have to track only one number, that is the likelihood statistics, and the smallest number is just related to that p value at the time n is smallest alpha, such that T alpha, now this T alpha is less than equal to n, and that's the p value. Now this test has two properties, and that is, now imagine someone stops the first time the p value falls below alpha. What does the amount to that is stopping at T alpha by definition? The T alpha is chosen that is guaranteeing the false positive, i.e., that is controlling these additional fluctuations. The time period of alpha is chosen in such a way that the fluctuations is controlled. So we first work out what is the range of these fluctuations, and then we set T alpha to make sure we have controlled them. And now if the user stops the first time it crosses alpha, it's exactly the same as controlling the fluctuation. That's not only the only rule for which we get false positive. No matter when the user chooses to stop, in an adaptive way, the false probability would be bounded by alpha. And how do we get this constant value? The test is by many of the professors. They have done a mixture sequential probability ratio test, and for run length they fix alpha, then T alpha is the first time you cross the two solid black lines for a particular constant. So for each alpha you get one of these pairs of black lines, and so as further you go the alpha gets smaller, and more further you go the black lines also they converge. So alpha gets smaller, T alpha gets the T alpha also gets larger, and alpha, that is the false positive, controls test control false positive and gives you detection. So it is good. It might give you detection eventually, but what if it takes forever to go there? So what we wanted to do was a relative to test. So we have to give up something for continuous monitoring of test. Now the question is, if the effect size is known in advance, in principle you should be able to do better by continuously monitoring, because you have just expanded your feasibility region. So with the knowledge, if you knew what the gap should be, so you are saying that I already know the gap, but practically you do not know the effect size. And the test that we design does not assume any knowledge of the effect size. So we compare how we do our test to a fixed horizon test using data from various softwares like Optimizely or Google standards. The ratio of how long a test takes and how long effect horizon test takes. So how do we do that? We use a sample size calculator to determine the sample size. You have to just play a little bit with the sample size. Now we can assume that I know what effect size is and I have a particular false positive that I'm trying to hit and a particular false negative that I'm trying to hit. That determines the sample size out of fixed horizons. I need to be able to meet the constraints. Now, and also I need to run it long enough that you can treat the effect size as true effect size. And we use that in a sample size calculator to work out how long will you run a fixed horizon test, and that's the denominator. Now the numerator is that we used our testing procedure on top of the same data, and ask when will you stop, or when is the first time the p value is crossed and like cutoff is crossed. So the robustness to not knowing the effect size and detecting an effect size of delta takes a run length proportional to 1 divided by delta square. So the penalty for guessing wrong above delta is very high. And an MDA that is two times, like 2x is too small to run length, that is 4x is too long. So we have other procedures in front of it like multiple testing, family wise error rate, false discovery rate, experimentation in the internet age, and there are different things that can be done. So there is always a trade-off that we already discussed. So this is nothing but the trade-off between how much time do we have and how much sample size we have. So the difference between what do I want out of my test. So why is this A/B testing so important? Because it measures the cause and effect, and it can provide you uh, a gold standard to predict the future. And there are tools like HubSpot, Google Optimize, and they are free of cost. Now let's take a practical example. Okay, it was too much mind boggling, but I hope that I'm able to explain. Now we have a scenario that there are five things: hero image, product, price, call to action. So in this scenario, what we try to do is that we try to test this, and that's all in the background. You just get a result, and you have a traffic, that is the number of customers you're diverting to what. So first we test the hero image, we change the hero image and we get a result. So we have a 12 weeks experiment for optimizing the maximum profits, and here we see that this one here conversion has got a higher rate, so we can choose a C image out of C. Now for 12-week optimization maximization problem, we do a simultaneous experiment. So out of two, how do we conclude that we will say that B version has a lower conversion rate, hypothesis. So we drive the traffic to other two versions and call it to action. For the call it to action, the variation has slightly higher conversion rate. So traffic allocation is to D variation. Now key decision variable is when do you say that you have enough evidence to say that you can conclude one of the variations has won. Yes, one of the variations is the winner. Now we can you have to keep doing it till 12 weeks, and allocation traffic as per profit and result on explore the explore first, or there is an epsilon first strategy. So most gains come from finding rare interventions with big effects, not precisely measuring small interventions with small effects. And for this score, 70% is 3 is a very good score, and you can like increase it or do it. So now what's the procedure? The procedure has changed a little bit from what we discussed in our previous slide. The problem statement or the goal of the experiment, we have to define that. What is the problem statement or the goal of the experiment? Hypothesis testing, design of the experiment, running experiment, and validity check. Now for design of experiment, I would like to highlight something, that we need to consider the experiment parameters, randomization, and user audience target. For audience target, we go in for a user funnel, and we try to understand that we are trying to target the visitors, the searchers, the browsers, on our website searchers or viewers, or the purchaser. And for running the experiment, requirement for what are the requirements for running the test? And for invalidity checks, we do for biases and errors if any, and for resulting decisions have to be made. And we have to understand that at this stage, when we are the design of experiment is very crucial stage, because you have to understand that this would define the success of the matrix. So you should take a audience that is measurable, attributable, that is the treatment cause has effect on the behavior, that what you are applying to your website should change the behavior of the consumers. Variability, that is, does the matrix has low variability that you can distinguish the treatment of control. And timely, can you measure the behavior in short term, because we are trying to see that if there is a revenue per day per user. So that is the revenue per day per user by big websites that happens. And then we have hypothesis testing, that is, so our hypothesis would be average revenue per day per user does not changes. And then we set our significance level or the threshold level to 0.05, that is the p value, and 1 minus beta, that is our statistical power, to 0.80, 80% of detecting an effect if an alternative hypothesis is true or not. And then we set the MDE, that is the minimum detectable effect, and the practical significance is set up at 1%. So after you have done the step 3 of designing the randomization units at user level, which population of users you want to target, like the purchaser, visitors, or the searchers. Once you have targeted the searchers, because we want the people who have tried to search our website, we want them to turn into purchaser. Now we determine the sample space, that is n, which is approximately equal to 16 times the variance divided by uh, delta square, that is difference between the control and the treatment p, 0.5 power to the test of 0.80. And step 4 is the duration, that is for 1 to 2 weeks. I hope that it's clear how we are going about the procedure. And then the next step is to run the experiment and compare the result of the treatment and the concept group. Now, when I'm comparing the treatment and the control group results, we have to avoid peaking the p-values, meaning that no decision should be taken before completion of the experiment, because that can lead to false positive. And then we have to check for bugs, glitches, like instrumental effects and various effects like like the latency time, external factors like holidays, new movers, economic disruptions, force majeure, competitions, recessions, COVID, and check for biases by doing the AA testing when both are homogeneous. Sample ratio mismatch is checked, that is the check for chi-square and goodness of fit. And if there is any novelty effect, that is segmented by the old and the new visitors, and then we interpret the results. Now the final decision is the launch decision factor. Now in launch decision we have to take two considerations, the primary and the secondary. When we may have a point at which the primary matrix may be increasing and the secondary may decline, so we have to check about the pros and cons of launching, cost of launching, and maintaining is if more than the anticipated profit. And if there is chances of like false positive, then we have to take care. So there are so many things that have to be taken care of. Just like 5 minutes more and this lecture would be over. Just bear with me, because we have to consider four critical elements now: the true positives, the true negatives, true positives TP, true negatives TN, false positive FP, false negative FN. With these we evaluate the efficacy of binary or multi-class classification models using matrices like precision, recall, sensitivity, specificity, and negative predictive value. So our exploration then takes us to the logistic regression, and that's a staple in the classification of model realm. Unlike linear regressions, straight line, logistic regressions uses a sigmoid function to predict outcomes which are typically binary, 0 or 1. Now the logistic model builds upon the core concept of linear regression, introducing the notion of odds and log odds, that is the logit model. This serves as a link function, enabling us to interpret our model coefficient. The role of threshold in model performance. Now, how does threshold impact the decisions? Now, in binary classification, the threshold is indeed a pivotal aspect. Now, when you are predicting the probability of an instance belonging to a particular class, a threshold determines at what probability you classify an instance as the positive class 1 or negative class 0. Imagine your email service has a spam filter that uses a classification model to decide whether an incoming email is spam or not. The model computer a score probability for each email representing the likelihood it's spam. If you set a high threshold, say 95%, the model will only mark very obvious spam emails, ensuring your important emails don't accidentally get flagged. However, this might mean some less obvious spam emails might slip into your main inbox. On the other hand, if you set a lower threshold, say 50%, the filter will catch a broader range of spam emails, but there's also a higher chance it might incorrectly classify a legitimate email as spam. In this scenario, the threshold determines the balance between ensuring you don't miss important emails, that is false positive, and ensuring spam doesn't clutter your main box, that is true positive. Adjusting this threshold affects the balance, representing the trade off in decision making. Now, one thing we need to understand is that how do we balance the true positive rate and the false positive rate? Now, the relationship between the true positive rate and the false positive rate will reveal a model's behavior across different thresholds. When we have a lower threshold, it classifies more instances as positive, leading to a higher true positive rate, but also a higher FPR, the false positive rate, as more negatives are mistakenly identified. Now, a higher threshold becomes stricter, classifying fewer instances of positive. This results in a lower TPR, that is missing some actual positives, and a lower FPR, that is fewer negatives are misclassified. The ROC curve shows how TPR and FPR change as we adjust the threshold. Even though both TPR and FPR can rise or fall together, now the key is how fast or slowly they change compared to each other. This differences in their rates is the trade-off we often talk about. A classifier's performance is considered optimal when it achieves a higher TPR without a significant increase in FPR. Hence, the top left corner of the curve is that signifies a high TPR and low FPR. So this represents the ideal balance between the two. So what is ROC curve? The ROC curve is a graph that shows how well a classification model distinguishes between two classes, like spam or not spam, at various thresholds. Now it lets you visualize the model performance at all possible thresholds, not just a single one. So how do you create a ROC curve? Predict probabilities. When you ask a classification model whether something is spam or not spam, it doesn't simply guess it. Internally, the model calculates a probability. Test different thresholds. Now, if the model directly classifies based on internal score, we'd have to set a threshold. For instance, you might say if the score is above 0.8, call it spam. But if it is 0.8 and it is at the right threshold, what if 0.7 is better, or 0.9? Track TPR and FPR. Now, the true positive rate and the false positive rate is about all of the actual spam emails. How many did we correctly call spam? How many did we incorrectly called spam? So FPR, the false positive rate, is about actual, not spam emails. How many did we wrongly call spam? Plot for each of the threshold. Plot the true positive rates on the y-axis and the false positive rates on the x-axis, and connect the dots to form a curve. Now, how to intercept it? Top left corner is best. If the curve is close to the top left corner, that's great. It means we have correctly identified spam without mislabeling many genuine emails. Maximum true positive and minimum false positive. Now, about the diagonal line, if the curve is above the diagonal line from bottom left to top right, our model is better than just random guessing, because the diagonal line means where TPR is equals to FPR. Area under the curve, that is AUC, the bigger the area under the curve, closer to 1, the better is our model. So area under the curve, what does it quantify? It's a quantify classifier performance. The ROC curve plots the true positive against the false positive rate over the various thresholds. Now, instead of assessing a model through the ROC curve visually, AUC curves, like area under the curve, summarizes it into a single numeric value with a higher AUC indicating superior model performance. Now, when we do comparisons of AUC, comparisons of model, we see that AUC is very important. A single AUC value offers quick comparison for various multiple models. The one with higher AUC generally excels in the classification when evaluated on the same data set. Now, effective with the imbalance in data set. So when there are imbalances in data set, it's effective. What is effective? AUC curve is effective in data set where one class is significantly dominating. Matrices like accuracy might not provide an accurate picture. So this area under the curve, which incorporates both the TPR and the FPR, serves as more reliable matrix in such instances. So when you interpret this AUC, now AUC at 0.5 implies that the classifier performance is equivalent to random guessing. That is like simple, akin to a coin toss. It corresponds to diagonal line front of from like 0, 0, 0 to 1, 1. That is on the ROC plot. Now, if 0.5 is less than AUC is less than 1, this indicates that classifier has outperformed random guessing. The closer the value is to the 1, the better the classifier is at differentiating between positive and negative instances. When we have this AUC at 1, a perfect classifier that is flawless distinguishes between positive and negative classes. It's a threshold value and seldom achieves real world applications. And so while we say that generating this ROC AOC curve for evaluating binary classification model is very straightforward, but when we try to grasp it, its underlying principles demands a little bit of more exploration. Now this journey begins with the foundation concepts of confusion matrix. This helps us to gauge the performance of classification of models and extend to nuances of like logistic regression, which is a corner step of classification modeling. Now, once we have understood this, we are now good at comparing models and we would be able to choose which is the best model. Now, initially, the ROC and the AUC curve is basically associated with binary classifications, and it has been extended in multiple classification problems as well. Now, how do we start in statistics? Bernoulli distribution, which is of success and failure. Then there is a Poisson distribution. Then there is an exponential distribution, e raised to the power minus lambda over lambda factorial. Then there is uniform distribution, normal distributions. So there was evolving of things, and then there is different log normal distribution and beta distribution, gamma distribution. So these all originated from Bernoulli and then went till by binomial and then approximation. So this is the basic foundation of how it is going to evolve in machine learning. So thank you so much for listening. Bye bye.